Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy instructor here at Foothill College in Los Altos, California. And it's a real pleasure to welcome everyone here in the auditorium and everyone listening to us on the web to this lecture in the 11th annual Silicon Valley Astronomy Lecture Series. This is a program dedicated to the public understanding of science, sponsored by 4 organizations here in the San Francisco Bay Area: NASA's Ames Research Center, a premier NASA Center for Education and Research; Foothill College, one of the top community colleges in the nation, where we offer courses both during the day and in the evening in many, many different disciplines; the Astronomical Society of the Pacific, founded in 1889, which is the country's oldest and largest public education organization in astronomy; and the SETI Institute, an organization devoted to the exploration of life in the universe and to both research and education about it. It's a great pleasure for me to be able to welcome tonight's speaker in the series, Dr. Helen Quinn. Dr. Quinn is professor of physics at the Stanford Linear Accelerator Center at Stanford University, and she was until recently assistant to the director of the Stanford Linear Accelerator Center for Education and Outreach. She tells me that she's recently retired, but not fully retired. She retired to dedicate herself to the issues of science education. She is now the chair of the National Academy of Sciences Board on Science Education and continues her work at Stanford on a national scale. Dr. Quinn has been elected to the National Academy of Sciences and was also former president of the American Physical Society, the country's largest group of physicists. She's won several awards for her research, including the Dirac Medal for contributions to the modern theory of particles and forces in the universe. And she's made a special point of sharing our modern understanding of particles and forces through her lectures and through her writing. Her book, her popular book, which I have here, is called The Mystery of the Missing Antimatter. It's published by Princeton University Press, and it's an engaging introduction to the kinds of questions she's going to talk to us about tonight. Dr. Quinn was born in Australia. She received both her undergraduate degree and PhD from Stanford and taught at Harvard before returning to the Bay Area. She's engaged in many different projects in science education, has been a very strong force in the direction of helping the public to understand science, and she's going to talk to us tonight about the many mysteries of antimatter. Ladies and gentlemen, it's a privilege to introduce to you Dr. Helen Quinn.
Well, thank you, and thank you for the applause. I'm here as an imposter because I'm not an astronomer and I'm not a cosmologist, but I'm going to talk some about cosmology. I'm a particle physicist, and that means I study the very smallest things in the universe. What is really fascinating to me is the fact that by understanding the behavior of the very smallest things, we can understand more about the biggest things. Not only astrophysical systems, stars and galaxies and clusters of galaxies, but also the universe itself. And so I'm going to really start with the cosmological connections of antimatter and talk about the particle physics sort of on the side as we go along, because it really is important to understand the particle physics in order to understand the universe. It's interesting to understand the particle physics from a particle physics point of view too, but I have an echo coming back at me. It's kind of annoying. However, let's start the slideshow here. And I also apologize. Particle physics doesn't make nearly as pretty slides as astronomy does. Okay. So there's 3 cosmological mysteries about the universe. The first one, what is dark energy, I'm not going to talk about. But that's fine because nobody knows the answer anyway. Okay, what is dark matter? We don't actually know the answer to that one either, but it is some kind of particle. Not the ordinary kind of particle we have in this room, but some other kind. And the mystery there is what kind of particle it is. And I put another question there because that's the one that relates dark matter to antimatter. And that is, how does dark matter die? If two dark matter particles meet one another, sometimes they both disappear, and out come an ordinary matter and antimatter particle. So it's one of the ways that antimatter may be being produced in space. Other side? All right. Maybe that gets rid of the echo. Yes, it helps a lot. Okay. So dark matter is one of the mysteries I'm going to talk about a little bit. Just for a show of hands, how many in this room have some idea what dark matter means? Yeah, you've had a good fraction of you have had some lectures on it. I'll tell you a little more about it as I go along. Okay, and then the final question, which is actually the fascinating one for us, I called the book The Mystery of the Missing Antimatter, but the real mystery is the existing matter. The fact is that there's any matter left in the universe today is a total mystery. And of course, if there weren't any matter, there wouldn't be any stars, there wouldn't be any planets, and there wouldn't be any us. So it's a mystery at the root of our very existence. And that's the mystery I'm going to spend most of my time talking about today. But since these mysteries are kind of related, I'll start. This is what we know. Now, how do we know it? There's an incredible concordance of evidence about the universe from many, many different experimental directions. This is not just theory. It's evidence and theory put together to give us a clear picture of what the universe contains. And it says, forget about what it contained 13.7 billion years ago. Today, it's 75%, 72% dark energy, 23% dark matter, and 4.6% atoms. Things that we know about that we call matter. That means all the stars, everything you see when you look out there, is a tiny fraction of the energy density in the universe. And I'm here to tell you that that tiny fraction is bigger than we can explain by particle physics. We would have expected more or less zero when we try to understand it. And I'll go through that story. The picture 13.7 billion years ago was just after the event we commonly refer to as the Big Bang. And at the time, the universe first became something we could make observations about. So I'll tell you more about that. And things have changed, but they haven't changed a lot. Except for the dark matter dark energy coming in, and I'm not. So the one thing that is the oldest thing that anybody can ever see is called the cosmic microwave background radiation. So there's 4 words there, and we're going to have to look at each of them. Cosmic means it's everywhere in the cosmos. Microwave, well, you know what that is. Most of you probably have a microwave oven. It just tells you the wavelength of the radiation that's coming. Background, again, because it's all over the place. And to start with, people didn't know what it was. In fact, when they first discovered it, they thought it was noise in their detectors. And they finally figured it out that it was something real. What it is the oldest light traveling through the universe since the time the universe first became transparent to light. The universe is expanding. It was hot and dense, so hot and so dense early on, that when atoms collided, they knocked one another apart and ionized. So instead of being a gas of neutral atoms, the universe was full of charged particles, protons and electrons separately. And if you have charges, then light can't travel. It bumps into the charges and gets deflected. So it's going all over the place and scattering off everything else and being absorbed and re-emitted. All of that going on in the very early universe until it expands and cools enough that atoms become stable. At that point, it becomes a gas of neutral particles, and whatever light is present at that time can now start its journey across the universe. And 13.7 billion years later, we see it coming from that direction, that direction, that direction, that direction. And the most amazing thing is it's the same in all directions to a few parts in a million. We can find, for those of you who know about relativity, we can find a frame of reference in which we look out at this light in all directions and measure its temperature, because it's a spectrum of light which reflects the temperature. The temperature is 2.7 something degrees Kelvin. It started out at the temperature at which atoms combine, which is 300,000 degrees Kelvin. But as it traveled, the universe was expanding, and it was stretching the wavelengths of the light. And so the light cooled to lower temperature spectrum. And now we see the 2.7. Okay, that's what we see. And here's a map of it. And you may wonder what all of this has to do with antimatter, but don't worry, I'll get there. So you may have seen this picture, those of you who know what dark matter is, because this is piece of the evidence. This is the universe when it first became transparent to light. The little red parts are a few parts in a million hotter than the rest. And the little blue parts are a few parts in a million colder than the rest. And you see this spotty pattern, and we understand the sizes of the spots, and we understand this map. It tells us many things. But among other things, we have to put that together with the laws of physics as we understand them and evolve the universe from here to here. All the structure we see today had to grow from those few parts in a million differences in density, which reflect themselves as few parts of a million differences in temperature in that radiation that's coming to us. And you can't get here from there without dark matter. You have to have dark matter in the mix. That's one piece of the story. The other piece of the story is that this whole structure, the one we saw here, the fact that we understand the sizes of these blobs and we understand the pattern, the kind of pattern we're seeing there, the pattern tells us that before the moment that we normally call the Big Bang, before this expansion of the universe that we observe today started on its gradual expansion, there was a period of very rapid expansion, exponentially fast expansion, which we call inflation. And that inflation will become important in telling the story of the antimatter. So that's why I needed to talk about this picture, because this picture is a major piece of the evidence that inflation happened. Okay, so what does it tell us? It tells us the universe underwent a period of exponentially rapid growth. That means whatever was there before this growth got diluted away. Whatever density of anything, if you get, and it's a factor of e to the 60th that the radius blows up. So the volume blows up by a factor of that cubed. And if you do a little arithmetic, you find that's a very, very big number. And so anything that was there before this inflation really doesn't matter for our story about the universe today. So we can follow the laws of physics for how the energy of this expansion got converted into particles. And those particles were radiation, they were dark matter, they were matter and antimatter. And they were all produced together at the same temperature. And therefore, the laws of physics say there were equal amounts of matter and antimatter produced. So the real mystery is, why today do we have matter around us and no antimatter, when the universe started with a process which must have produced equal amounts of matter and antimatter? Now, I'm talking about antimatter as if you all know what that is. Don't worry, I'll get to that too. One of the things we know about matter and antimatter is that when they meet, they can both disappear and give you just radiation. You can convert matter into energy, pure energy. I mean, matter is energy too. And the energy in the matter turns into energy and light when they collide. So this is what happened as the universe expanded. It was full of particles and antiparticles, but when they met, they could turn into photons. And then because the universe was expanding, the photons were getting stretched in their wavelengths and therefore lowered in their individual energies. And so when they recollided the photons, they couldn't make the matter and antimatter again. So gradually, all the matter, well, all the antimatter and most of the matter disappeared. And what we have left is just the excess matter over antimatter at some early point. But according to this, there shouldn't have been any excess. So that's what we have to try to explain. How they somehow must have gotten out of balance. When did that happen? How did that happen? That's a question of physics. And the real question of physics is much more detailed than that. Can we explain how much they got out of balance? We actually know how much they got out of balance. Because when the matter and antimatter annihilated, they made photons. That's the photons, the entropy that's in that cosmic microwave background radiation. So we can actually calculate the ratio of matter to photons in the universe today from observation. And now we have to explain how the imbalance gave us that ratio. And the sad fact is, given all our best theories of physics today, we can't. So we have to modify our theories of physics. And that's what makes the world interesting, right? We don't know everything yet. We have to learn some more in order to answer this question. Okay. Well, I said it was a small imbalance. Now I'm giving you a number. It's actually 1 part in 30 million. All of the matter in the universe today is 1 part in 30 million of the matter that was there right after the Big Bang. And that has to be the difference between matter and antimatter that we get in our calculations. That's a real puzzle. Okay, what do we know? In order to try and calculate this, we have to go and look at the laws of physics for matter and for antimatter. What we know is, first of all, antimatter exists. So in 1928, Dirac wrote an equation. His equation, he had some reasons why he wanted to do things this way. They weren't necessarily the right reasons. But today we can say the reason we needed this equation, not the one that was existing before, which is called the Klein-Gordon equation. So Klein's equation could have been, as far as Dirac knew, the right equation for electrons, but he didn't like it. So he wrote a different equation to explain electrons. And what he did was wrote an equation that applies to all particles that obey exclusion principles. So any of you who learned chemistry know you can only put 1 electron in each state. You can't put 2 electrons in the same place at the same time doing the same thing. They just won't do it, right? And Dirac's equation has that property for electrons. So it is the right equation for electrons. The amazing thing about this equation, written down in 1928, was that it predicted not only electrons, but particles exactly like electrons, but instead of having negative electric charge, they had positive electric charge. We call them positrons. Not only that, it predicted for every particle that has this property like electron of not wanting to be 2 of them in the same place, every such kind of particle has to have its antimatter mirror twin. So if you have a proton with a plus charge, then you have an antiproton with a minus charge. If you have a neutron, it has 0 charge, but it has an antineutron with a 0 charge. But it's opposite if you go down to the level of the quarks inside, because the quarks inside a neutron have charges, and the quarks inside an antineutron have the opposite charges. They're antiquarks. So we know all through particle physics, all of the particles that make up any kind of matter have these mirror twins. We can make these things in the laboratory. We make anti-electrons, positrons. We make antiprotons. We've even made a few, very few, anti-hydrogen atoms. So antimatter exists. It happens in the laboratory all the time. It happens wherever there are high enough energy collisions to provide the energy to produce a particle and its matching antiparticle. That means it also happens in space where high energy particles are. And lots of objects in space make jets of high energy particles coming out of them. So there are places in space where we ought to see antimatter, and we do. But the antimatter that gets made in this matter-dominated universe generally disappears very quickly. Why? Well, because if you have an antiparticle and meets a particle, they can both turn into photons again. So if we make matter, antimatter in the laboratory, we pretty quickly lose it. We can keep it going in a storage ring that is vacuum, so there's nothing for it to bump into in the storage ring. We pump the inside of the storage ring down to 10 to the minus 12 atmospheres, and we keep the positrons going around the ring for some hours. But if ever they bump into the wall or bump into a stray atom of gas, we're likely to lose them. So it's real stuff, and this process of the two of them disappearing is the idea behind the Star Trek antimatter drive, right? If you have particle and antiparticle and you put them together, you've converted all of the mass into energy. And you know, we say nuclear energy is great because there's more energy per mass coming out in a nuclear reaction than in a chemical reaction. Well, imagine the reaction where all of the mass goes into energy. That's great, except for the fact that we have to make the antimatter first and figure out a way to store it so it doesn't bump into anything and disappear before we're ready to use it. So antimatter drives are a great science fiction idea, but I doubt we'll be using them for any real rockets anytime soon. Now, the other thing you need to know about matter and antimatter is that the laws of physics for matter and antimatter are very, very, very similar. They just kind of mirror images, one of the other. In fact, in Dirac's equation, there were exact mirror images. We know today there's a tiny, tiny asymmetry in the laws, but it's mostly exact mirror image. So I'm going to give you the first recognition of this mystery, as far as I know, is Pauli, who in 1933 wrote a letter. Pauli was good at letters. You know, when Pauli also was a person who had the first idea of the existence of a particle called the neutrino. And he didn't go to a meeting, he wrote a letter saying, "Dear radioactive gentlemen, I suggest this particle exists, but I'm too busy going to a ball to come to the meeting." Or he actually said, "Unfortunately, my attendance is required at the ball." But this letter, also to Heisenberg, who was one of the other people in this gauge, says, "I do not believe in the whole theory. The whole theory is the theory of antimatter. It's an old-fashioned name for it. Don't worry why. Since I would like to have the asymmetry between positive and negative electricity, in other words, between positrons and electrons, in the laws of nature, it does not satisfy me to shift the empirically established asymmetry, the fact we live in a matter world with no antimatter anywhere around, to one of the initial conditions." So Pauli says, this is a puzzle, and I don't want to answer it in a certain way. I don't want to say, well, it's always been that way. The universe started with this imbalance. And Pauli was right, because now we know with this inflation theory that whatever the universe started with doesn't tell us anything about the way the universe is today, because it blew up so fast that what it started with got diluted away, and something got produced later. So Pauli actually stated the problem, stated we had to have the asymmetry in the laws of physics, and said he didn't like initial conditions. Today we have a stronger reason. We know they don't work. But that asymmetry in the laws of physics, that tiny difference between matter and antimatter, wasn't discovered until 1964, where we found a particular process where we could see there had to be a difference in the laws of physics to explain that process. And the last almost 30 years of my career have been working to develop and then exploit a facility at SLAC, which we called the B Factory. I'm the theorist. I didn't do any of the building, but I worked with the people who did, because this facility was designed to really study in detail the difference in the laws of physics for matter and antimatter for quarks. And it has done that study and come up with answers. So let's go back to the universe, and then I'll tell you about the asymmetries in the laws. There are answers people want to give to this problem that just don't work. The first one I've told you doesn't work is the universe has always been that way. Somehow it started out with an imbalance, and the excess matter has always been that excess. First of all, it's ridiculous. What a tiny number to adjust as an initial condition. If you give me enough initial conditions, you can't prove that the universe didn't start 5 minutes ago. Everything very finely tuned, so your brains think you've been sitting here for more than 5 minutes, but in fact, that's ridiculous, right? So complicated initial conditions are kind of an avoidance of explaining things by physics. And as anyway, with the inflation, the e to the 60th factor of expansion that happened in the very, very, very early universe, it doesn't work. A second answer would be, well, somehow there was matter and antimatter and they were equal, but somehow they got sorted out. So think of that of a mixed up jar of black and white marbles, and you shake them long enough and you get big regions of white marbles and big regions of black marbles. And we just happen to live in one of the white regions. Well, again, that's physically ridiculous, right? You can shake that jar as long as you like, and you will not get big regions of white marbles and big regions of black marbles. You may get little collection, little patches, but you won't get this huge region which is all white and another huge region which is all black. And we can tell when we look out, if we were in a matter region and somewhere out there in space there was an antimatter region, then the cosmic rays of our region meeting the cosmic rays of their region, at the surfaces between these two regions, there'd be matter and antimatter meeting one another, annihilating, and the surfaces would glow. And so people have studied that, and they figured we could detect those surfaces out to about a third the size of the visible universe. Well, take two things, matter and antimatter, with almost identical laws of physics. There's no way it's going to sort itself like that. It just violates all laws of probability. You cannot get a mixture to sort itself on a scale the third the size of the visible universe. It does not happen. So that answer doesn't work. Then the other answer is, well, this imbalance is just, I said thermal equilibrium said matter and antimatter had to be equal. But we all know in any thermal system there are small fluctuations around equilibrium. So how big could that be? Well, people have done that calculation. The answer comes out much, much too small. Cannot do it that way. So we have to find a mechanism, a time and a place in the history of the universe where this imbalance happened. Now Sakharov, great Russian physicist, told us what we have to look for. He said you have to have three things at once. First of all, if you want matter and antimatter that are in balance to get out of balance, you'd better not have a conservation law that says you can't change the relative amount of matter and antimatter. That's pretty obvious, right? You want to change something, you better not have a law that says you can't change it. Well, actually, our laws of physics, most of them have that conservation law. So this already tells us that we're dealing with physics at the edge of things we understand. It's not quite true that we have that conservation law. Under very, very high temperature conditions, that conservation law doesn't operate in our major theories today. So we know that condition's okay. In the early universe, we had very, very high temperature conditions. That one's okay. We have to have the asymmetry in the laws of physics. If the laws of physics are exactly the same for matter and antimatter, there's no way you can get them out of balance. Because any process which gets an imbalance one way is exactly matched by some other process which gets an imbalance the other way. And those two matching processes will always cancel one another out. And so equality will be the rule. So you have to have some place in the laws of physics that are different for matter and antimatter. And finally, because I told you in thermal equilibrium, because matter and antimatter particles of a given type have exactly the same masses, in thermal equilibrium they have exactly the same population. So you better find a place in the history of the universe where thermal equilibrium doesn't rule the day. Because otherwise, no matter what possibility of imbalance there is, the laws of energy wants to balance itself out in all its modes, so we get a uniform temperature in the room, we get a uniform density of matter and antimatter too. So we'll have to look for some time in the history of the universe when all three of these conditions can play out. Now we have to go and understand the laws of physics. So we've got the possible asymmetry pinned down. So this is a very quick summary of everything we know about the laws of physics for particles. First of all, there's the zoo. Which particles do we have? We have quarks. Protons and neutrons are made of quarks. Whole nother lecture about that story. We have leptons, things like electrons and positrons. We have the particles that mediate the interactions. And when we put together the theory with all the particles we know, it turns out the rules of the mathematics of that theory only allow us one place where we can put in a difference for matter and antimatter. The theory kind of almost automatically enforces mirror image laws for matter and antimatter. And there's only one parameter in the theory of the quarks. Now, that theory is what's called the standard model. We already know it's not complete. Why do we know it's not complete? Well, first and most obviously, it doesn't contain any particle that could be the dark matter. So we have to extend it to have dark matter. It doesn't contain masses for neutrinos. And we now know that neutrinos have masses. So we have to extend it to put in the neutrino masses. And it doesn't contain enough matter-antimatter asymmetry, because when we take that one place that we do know there's an asymmetry and we try to play it out in the history of the universe, as I will shortly do, it doesn't work. And so we know this theory is incomplete. That's fine. Our theories are almost always incomplete. This theory is quite amazing in what it can do, but I'm talking today about some of the things it can't do. Okay, just to tell you that this is not just all theory and people waving their hands. This is the result of the bee factory, or two bee factories actually, one here at SLAC and one in Europe. Don't worry about what this is. What I'm telling you is every color on this plot is a different experiment. And they're all plotted against this theory that has one parameter, that is the area of that little triangle in the middle. That tells us there's an asymmetry. And we overlay all these different experiments, and the little red ring shows the place where they all agree with the theory. We can fit all these different experiments with one parameter, one area, one place. So if the triangle turned flat and the peak of the triangle had to lie on the straight line at the bottom, there'd be no asymmetry. So this diagram is evidence from many, many years of experimental work by many, many people. Babar at SLAC is a 10-nation international collaboration of some 500 physicists from all around the world, and an equivalent number in Germany, working very hard to make all the measurements, and then some of these measurements come from other experiments too, to give you plots like this that say, yes, our theory works, it fits everything we've measured, and it tells us this is the size of the difference in the laws of physics for matter and antimatter. That's Great, so we know that parameter. Now we can take that theory and we can say, how could we calculate, where could that parameter affect the universe? And I'm going to talk about a second possibility, because now that we know neutrinos have mass, it turns out in the neutrino part of the theory, there's room for some more parameters. We don't know those ones yet. So we've got a little more freedom to play around if we don't play with the neutrinos. But let's first try and do it with the quarks. When we do it with the quarks, it's called baryogenesis, because what we're trying to do is make particles like protons and neutrons, and we have a name for those, they're called baryons. And it comes, so I'm going to tell you that story first, and then I'm going to tell you what we have to do to make that story work. And then I'm going to tell you the leptogenesis story, because I don't know which of these stories is right. Nobody does. We're going to have to figure it out. So I said we had to get out of thermal equilibrium. How do you get out of thermal equilibrium when you're in thermal equilibrium? Well, think about a phase transition. Think about a bubble forming. Inside the bubble we have one phase, and outside the bubble we have the other phase of a gas. Say a gas and a liquid. The bubble, if the conditions are right, that the phase inside the bubble is the energetically favored phase, then the bubble will grow. And eventually we'll have the universe in its current condition. So as the universe cooled, such a thing happened. It's amazing, isn't it? Thinking about the universe going through a phase transition. What was changing? What was changing was the masses of all the particles. The conditions in the early universe had all of the particles effectively massless. And then, as it cooled, it got to a condition where the mechanism that drives masses for quarks and leptons turned on. And that was a phase transition. And that turning on of the masses of the quarks and electrons formed in some region in space. And then that bubble grew very, very rapidly. But as the wall of the bubble is sweeping through space, there's no thermal equilibrium around a transition going on. Something's changing. And if the wall of the bubble is such that particles can get through it a little bit more easily than antiparticles, then inside the bubble you can have an imbalance between matter and antimatter. Even when outside the bubble, the processes are going on which can change the balance of matter and antimatter, and thermal equilibrium is keeping them equal. So inside we have masses. Processes which can change the balance are essentially totally vanishing. They're so suppressed we can say they never happen. Outside the bubble we don't have masses. The processes which change the balance keep happening, and they keep thermal equilibrium equal amounts. But getting through the wall makes a difference. It actually is a story which fits together with everything we know, and we can do the calculation and we can find out how much matter, excess of matter over antimatter we get inside that bubble. And the answer is not enough. That little triangle was too small. Now we can fix it. So this is the whole story I've been telling you. I won't I'll just skip that slide because I told you it all. The standard model parameters, if we do the standard model, there's two things wrong. First of all, the wall of the bubble isn't so well defined. You've got to have what's called the first order phase transition to have a clean bubble wall in between the two different phases. And if it's not such a sudden transition, there's not such a clean wall, and the whole story doesn't make any sense. Secondly, we can change the theory. We can patch the theory. We can add things into the theory and get back that bubble kind of transition. But then, even with that extension to the theory, the asymmetry we know about is simply not enough. We can change the theory for that too. We can make the extra things we put into the theory to make the bubble wall come in can also give us ways of putting extra asymmetries into the theory. So it's possible to make this story work by extending the theory. And maybe that's still the right answer. I don't know. What we want is more evidence that will point us in the direction of which extension of the theory is the right extension. We don't have that evidence today. So the other story, just to be even-handed, we've got to tell that one too. We know even less about this story. Okay? Neutrinos are particles. How many of you have never heard of a neutrino? Be honest. Okay, there's a few hands up. That's not surprising. They're particles, they're going through this room all the time, but none of them ever stop to talk to you, so you don't notice they're there. They're very weakly, they only interact weakly and gravitationally. They're made when there's a process that happens inside nuclei. It's part of radioactive decay chains, where a neutron turns into a proton plus an electron plus a neutrino. And that is the particle that Pauly suggested in his letter when he said he was too busy to come to the meeting but had to go to the ball. So it's a very light particle, but we've recently discovered that indeed they have masses. And if they have masses, we have to extend our theory to put the masses in it. And when we do that, there's room for some asymmetry between matter and antimatter in the neutrino story as well as in the quark story. But we haven't measured enough. We don't even know what the masses are. We only know mass differences. In fact, we know differences of masses squared for the neutrino. We know there's 3 types of neutrinos, and we know the differences between the masses. It's not enough to give us all the answers here. Just to show I'm talking from evidence again, I'm putting some evidence here. What's the evidence? These are neutrinos that come from the sun. I told you a kind of process that makes neutrinos. Well, the processes in the middle of the sun that make all the energy of the sun that we see also make neutrinos. So when we make a model of how the sun works, or any other star for that matter, but the sun is the closest one, so we can measure more about it, we can predict how many neutrinos should be coming from the sun. And for a long time, it was a big puzzle because we didn't see the right number of neutrinos. Well, now we've done experiments that look not just at the first kind of neutrinos, which are called electron neutrinos. They look at the second kind and the third kind as well. And these are the experiments, the sloping line of the experiment that tells us the sum of all the types of the neutrinos. And the vertical line is the experiment that tells us how many electron-type neutrinos we're seeing. And the circles here say we're seeing some of each. And the only way we can be seeing some of each is if neutrinos have masses. And the ones with definite mass are a little bit mixed up from the ones that I called electron type and muon type that come with the different processes. So in the sun, we make electron type, but when they arrive here, they're not just electron type. They're a mixture of the other types. So this is all data. This is also a completely different experiment. Neutrinos get made because high-energy particles hit the top of the atmosphere. They make excited states of protons. They make particles called pi mesons. Pi mesons decay, and they make some neutrinos, among other things in their decays. And we can count how many electron type and how many muon type neutrinos we ought to be seeing from those decays. And what this is saying is we don't see the ratios expected unless neutrinos have mass, and the mass ones are mixtures of the named ones. Then we can explain the data. So there's now several different strands of data, and it tells us these differences of mass squared. We don't even know. So that we know there's one small difference of mass squared and one large difference, but we don't know if it looks like this or like this in the spectrum of masses of neutrinos. So there's lots still to be explored about this question. So the story. In order to put neutrino masses in the theory, the easiest way to do it is to put another very heavy particle in the theory that's kind of a cousin to the neutrinos. It's a cousin because it's quite different, it's very heavy, but it has neutrino-like properties, and it's a little bit mixed up in the story of the neutrinos. And it's responsible for giving them their masses. Now that particle is a very peculiar particle because it doesn't have any kind of interaction at all except gravity. And that means there's no way of labeling particle from antiparticle for that particle. It's a particle which has this exclusion rule, but the particle and antiparticle are totally identical. And so it's a particle that doesn't know matter from antimatter. And it turns out in its decays it gets a little bit mixed up about how much matter and how much antimatter it makes. If you have this asymmetry in the neutrino sector laws, this particle's decays can make uneven amounts of matter and antimatter because of the asymmetry in the laws. And these particles are made, and if such particles exist, like everything else, they're made in that hot early universe. And then when they decay, they can create the imbalance. So that's a very shorthand version of that story. Again, we can make the theory work. We don't know which of these answers. Both of them require us to extend our current theory. Both of them require additional things we haven't yet observed. So obviously, from a particle physics point of view, there's more work to be done. Let's go back to antimatter in space. I wanted to come back at the end here and make a linkage between antimatter and dark matter, because it's really quite fascinating how all these pieces keep fitting together and telling us things we didn't know, right? I told you there's very little antimatter out there because this matter around, it all gets annihilated and turned into photons. So the only antimatter in space is antimatter that's being made right now in space. That's where we see it. So we see it where there's high energy jets of particles coming out of, for example, quasars. We see it where there are high energy objects in space. We see antimatter in space. And so we have to make astrophysical models of all the possible ways we could be making antimatter in space, and then match that to our observations. And I'm going to show you some slides from a talk. This is a talk that was given at SLAC like 2 weeks ago. So this is the forefront of theoretical speculation right now. And Catherine Zurek is a young physicist from Michigan who was one of many carrying on these speculations, but she nicely gave me her slides so I could show them to you. And this is what we're looking at out in the universe and trying to explain, but haven't yet got right. We may not have the experiment right, we may not have the astrophysics right, and we may not have the particle physics right. But we're working on trying to get them all to agree with one another. And at the moment, they don't. So what am I showing here? There's ADIC, Pamela, and Fermi Gamma Ray Space Telescope. 3 space experiments looking at different things. So ADIC and Fermi Gamma Ray Space Telescope are looking, they can't tell matter from antimatter. They're just looking at charged particles. So they're looking at electrons. And they're asking how many electrons or positrons are we seeing out there? And people started getting excited, and I'm showing this data, although we now have pretty good conviction it's wrong, just to show you uncertainties can happen. Gave us this little funny bump in the spectrum, which no astrophysics could explain. And so particle physicists started jumping up and down and saying, this is matter and this is dark matter annihilating and giving us matter and antimatter in space. Well, part of the reason they were jumping up and down was this other experiment over here, which is called Pamela. And that is actually, I'm sorry, I was told I mustn't go over there because I get out of the camera. So to the people on the camera, they can't see that anyway. It's going up and the line is going down. The line is the estimate from astrophysical sources of antimatter in space. And the data is the evidence for positrons in space. They don't seem to agree with one another. So again, maybe there's some other process that isn't astrophysical making this. Or maybe we just don't have the astrophysics right yet. Or maybe the experiment isn't all that right, because let's look at this and this. The data in the top plot is also in this plot. It's very faint. So that faint data is the data from ATIC, and the very small error data coming along in the band below, which doesn't have that bump in it, is from the Fermi Gamma Ray Space Telescope. It's higher precision data, so we trust it better. And it says that bump isn't there. But look, it still doesn't really quite agree with the expectation from astrophysics, which is the dotted blue line. So again, people are trying to explain these discrepancies. And one way to explain these discrepancies is to make theories of dark matter that would produce these electrons and positrons in space. My guess is that's probably not the right answer. We don't understand the astrophysics all that well. Changing that dropping line to a slightly flatter line from astrophysical sources, as Catherine says on her next slide, she says it could be some nearby supernova remnants that change the astrophysical distribution, or it could be some kind of, these plots are a particular model of a particular theory with a particular kind of dark matter in it. She can fit all the data that way. So you can fit the data by making up theories of particle physics, but we don't know that you can't fit the data without the particle physics. So what does this tell us? When you have a situation like this, you can say it's a clue, it's a pointer in a direction to look, or you can say it's a constraint. Certainly we know, once we have these experiments, we better not have a theory that makes more antimatter than is there. So that's a constraint. You've got to stop making theories that give you too much antimatter in space, right? And you kind of develop on both fronts at once. The astrophysical modeling gets more refined. It needs particle physics to do astrophysical modeling too, by the way, because you have to understand particle processes in high-energy astrophysical objects. And the particle physics modeling gets more refined, and gradually these things get sorted out. So I'm just putting that out there to say this is work in progress. There's lots more to learn here. But antimatter in space may be one of the ways we'll eventually be able to learn something more about dark matter. And that's where I'll stop and let you start asking questions. Oh, I thought I'd just give you 3 things to remember, because I said an awful lot of things. So 3 things to remember. Antimatter exists. It's rare except where we make it, or where high-energy processes make it. The matter-antimatter imbalance that gave us a chance to exist here in the universe, we don't understand it yet. And finally, dark matter annihilations may be a source of antimatter, so antimatter may be one of the handles that helps us understand dark matter. Thank you. Go ahead.
Can you hear me? Okay.
Yes.
I have a couple of questions. One has to do with if there is, say, a antimatter galaxy, and not talking about boundaries between matter and antimatter and annihilation of cosmic rays, but if there really was a galaxy that's pure antimatter, there's no way we can tell with the light coming from it that it is made out of antimatter. Is that true?
Galaxies have more than light that come from them, right?
Yeah.
Galaxies have cosmic rays that come from them. They have particle jets that come from them. There's all kinds of stuff in space. Space is not empty, right? So around that galaxy, there'd be a glowing surface where the matter and antimatter regions of space collided. Right? And so the story I told, it doesn't matter how small the antimatter region is, that surface is going to be visible. Well, if it were really, really tiny, we couldn't see it. But anything as big as a galaxy. It's true the light would be no different,
That's what I-
absolutely.
yeah.
And the physics of the galaxy would be no different. Stars, anti-stars would form, et cetera, et cetera. You can imagine the whole thing, and the laws of physics would say, yes, that could work. But if it were to exist, in order for such a galaxy to exist, there'd have to be a large region of space populated only with antimatter.
Okay.
And that would run into the problem of the surfaces that I talked about.
And I just have two more short questions. I know you mentioned they can produce...
I think you need to go to the back of the line and
Oh.
let somebody else ask the question.
Sorry.
You mentioned at one point that there was a phase transition in the early universe at which point particles took on mass. Could you expand on that a little bit?
Could I explain it a little
Is that due to
further?
the Higgs field, and
It
how
has
long
to-
after the
yeah, so it's-
after the Big Bang did that happen?
This is a fairly technical story, but we have, and also one that's not fully explored to the end at this point. When you write down the standard model of particle physics, it's a theory in which there's a symmetry which enforces that all particles have zero mass. And the only way you can get around that is to somehow have what's called spontaneous symmetry breaking. Now that's not such a mysterious thing. If I stood a pencil on end, there's a perfect symmetry around, of directions around the pencil. But the pencil's got to fall in some direction, and that breaks the symmetry. Right? So if there's a lower energy state which doesn't have the symmetry, even if the equations have the symmetry, you can have a ground state that doesn't have the symmetry. Right? And that's the way it is with these equations of the standard model. And the thing, which is like the pencil falling, is called the Higgs field. And the Higgs field gets a vacuum expectation, and it gets a value throughout space, which, I mean, the value of the Higgs field is a mathematical statement because that condition is what we call nothing, right? So it's not something we can measure, but the interaction of the Higgs field with the particle masses, with the particles, gives them their mass.
And how long after the Big Bang was that?
How early? At what time? Tiny, tiny fraction of a second after the Big Bang. It cooled enough for that to happen.
Thank you.
Is it necessarily the case that for matter, antimatter type of reactions that you have to use mass? So mass is actually energy in disguise. So
No,
I'm asking.
it's not energy in disguise. All energy is mass, and all mass is energy.
Yeah.
There's no disguises here.
So you could effectively then have light with anti-light and have the light go against the anti-light and then have nothing result? Is that
Well, no,
doable?
because energy is conserved, right? So if you have some light, actually anti-light and light are identical because, again, light doesn't have any electric charge or any quantum numbers that differentiate light from anti-light, and that's not a problem. So for absolutely neutral things, particle and antiparticle are the same. So light plus light can give you matter plus antimatter. Or matter plus antimatter can give you light plus light. And that happens, and we do it all the time in the lab. It's no big deal. But the energy always stays around in one form or another. Right? So you have to have enough energy in the light coming in to make the particle and antiparticle. I'll tell you how we do it at SLAC. We take a beam of electrons down the accelerator, and then we take them out, and we slam them into a block of tungsten. Now, we've got high energy electrons moving through a block of tungsten. Because they're high energy, they penetrate inside the tungsten atoms, and they feel the high electric field of the nucleus of the tungsten atom, and they get deflected. So that's the first photon, is they're interacting with the electric field. When they're deflected, they radiate a photon and it makes an electron and a positron. So we send in an electron and we get out 2 electrons and a positron. And they're all moving together. And then we put some magnets, and in a magnetic field, electrons turn that way and positrons turn that way. And we can collect up the positrons and bring them back to the beginning of the accelerator and send them down. And we do that every day. when SLAC is, well, when we were running high energy physics experiments at SLAC, which we're no longer doing, we were doing it every day.
That's
But
really
so
cool.
it's
Thank
just
you.
a conversion. Like any other energy is all the time transforming itself from one form to another, right? When I pick up a book, I'm transforming energy that I've got in my body into energy of the gravitational potential energy of that book lifted up. So energy is always transforming from one form to another. And the matter-antimatter turning into radiation is just another one of those transformations. Nothing very mystical about it.
Is it likely or possible that the Large Hadron Collider will provide us some more insights into this issue? And if so, could you speculate on what they might be?
When I say we can extend the theory, that almost always means we add new heavier particles. Why? Well, because we can't add new light particles, we would have seen them already. So we add new heavier particles, maybe we find them at the LHC because it's looking in a region we haven't looked before. And many of the theories, and there are reasons for speculating as to what the masses of these new particles should be for different reasons. For example, candidates for dark matter, we may be producing those at the LHC. We probing the details of neutrino physics, not at the LHC. So understanding extensions of the theory, yes. Understanding the specific pieces of the extensions that have to do with this story, maybe, in some of the cases. But it won't tell us the whole story. There's more needed to be done.
Thank you.
So you've described this interesting problem of the imbalance between matter and antimatter, and I was wondering, is there a similar problem for dark matter as well, or is it we just don't know?
There's so much we don't know about dark matter that the question doesn't even make a whole lot of sense yet. Right? We don't know whether dark matter is one of these things where the particle and the antiparticle are identical, or whether it has some kind of dark charge which doesn't talk to our photons or doesn't do anything with the kinds of interactions we know about, and has its own set of interactions, which we know must be very weak, but there could be some. And then we could have matter-antimatter stories in the dark matter too. But it's just so far beyond what we know about dark matter at the moment that it isn't something people speculate much about.
Thank you.
I heard you talking about the probability of the regions of the large regions of just matter and
Sorting it
antimatter.
out, yes.
So I was wondering, because the universe inflated by a factor of e to the 60th power, wouldn't these regions inflate as well? And I think it is possible for the large regions of matter and antimatter to exist.
Well, what happened is the inflation happened, and then the matter and antimatter got made after the inflation.
Oh.
So
Oops.
then we had this mixture. And now the problem is, how do you unmix it? And it's actually very hard to unmix mixtures.
Yeah.
Somebody needs to take the microphone off the. There we go.
If you ever capture antimatter, how will you study it?
Well, we do. We make it, and we capture it in our accelerators, and we study it by bumping it into other particles and seeing what happens. That's actually how we study almost everything, right? We see how it interacts and what it does. And so we do a lot of experiments with particles and antiparticles in our accelerators. And that's how I can say we know these laws of physics, and we know it's the same for matter and antimatter. It's all based on experiments where we did study it. You can also put it up again.
Is there a reason why our universe is a matter universe and not an antimatter universe? Is it just a happy accident that it went in one direction and not the other? And if there are other universes out there, is it possible that one or more is an antimatter universe, and what we're calling electrons, they're calling positrons, and
It's worse than that. First of all, whichever direction it went, we would have called that one matter. So the fact it's matter and not antimatter is because we saw this stuff and we called it matter. And then when the other one came along, we had to invent a new name for it, so we called it antimatter. So that's just a matter of nomenclature.
so is it something about the asymmetries that makes it go in one direction or the other?
So we can devise it so it goes that way, yes. But that's not, I mean, the difference is really tiny, and figuring out the sign of this effect is a detail of the theory. So we can certainly make the theory work the right way once we know which way we want it to go, right?
Thank you.
There was another part to your question, though, about other universes. And the answer is, first of all, as soon as we start talking about other universes, we're talking metaphysics and not physics, because we cannot observe other universes. So we have physical theory. The theory we work with can suggest what possibilities there are. So we take the mathematics that explains our universe, and it's very interesting to speculate what it says about the possibility for universes that have no connection to our own. And it seems very likely that there could be such things, and that they could have entirely different physics, not just different matter and antimatter in different imbalances, but different particles, not the ones we know. Different symmetries, not the ones we know. The laws of physics could have come out differently in different universes. And we don't, but all of that is what I call mathematical metaphysics. It's based on taking our theories and extending them to ask questions for which we will never have experimental tests to the answers.
Okay, I want to see if I have my understanding right. Dark matter could really be called invisible matter, and it's a thing whose gravity holds together galaxies and clusters of galaxies so they don't fly apart. And if dark matter self-annihilates, or maybe we don't know if it will,
do it very slowly, or there wouldn't be enough of it around today.
But things could eventually kind of fly apart. Galaxies come apart, clusters of galaxies come apart as the dark matter self-annihilates.
No, actually, the question is not, I mean, the galaxies their motions would change if they didn't have the dark matter in them. But at least some part of them are gravitationally bound even without the dark matter. Right? Some of the outer things might not be, but the system is gravitation, the inner part of the system is gravitationally bound anyway, even without the dark matter. But we needed the dark matter to get them to form. The gravitational pull to get them enough together to start forming needed the dark matter. You also need the dark matter to explain the motion of the outer stars when a spiral galaxy is turning. And if you could sort of suddenly extract the dark matter, those outer stars would no longer be bound gravitationally. At the speeds they're moving, they go flying off. Okay, but of course we can't.
At this point in the history of the universe, is the degree of asymmetry between matter and antimatter increasing, or is it relatively stable, or? It's
a static thing.
Okay.
Right. Once we went through the phase transition, and this is true for either the leptogenesis or the baryogenesis story, once we went through the phase transition, we live in a universe where there's essentially a conservation law. Okay. As far as we know, we have never seen, I mean, this is a conservation law which says protons can't decay, right? Because if a proton, say, according to the laws of conservation of energy, a proton could turn into a positron and a photon, right? And that never happens. What do I mean by never? Well, we know the half-life for a proton is greater than 10 to the 32 years under the current conditions in this universe. So balance between matter and antimatter, we can't get rid of matter and we can't make antimatter in isolation. The only processes we have today keep the balance. It's only in the very early high temperature universe that there were processes that could change the balance,
Thank you.
as far as we know.
Shall we say only the people who are standing?
Okay, if you're already in line, you can ask a question. Otherwise, it's a cutoff.
Okay. So exploring dark matter, basically annihilating or converting into a particle and an antiparticle, just wanted to understand that in a little bit more depth. Is it a very lengthy half-life that dark matter has for a decay?
Yeah, dark matter has a very, so dark matter could decay and it could annihilate. It's two different things. Right? Because one particle decays, two particles annihilate.
Okay.
Okay? But either of those processes have to be very rare and slow. And they only happen in the places where the dark matter is densest. The annihilations only happen in the places where dark matter is most dense, like the center of a galaxy. Perhaps there's some dark matter annihilations going on.
Do we believe we've observed that, or is it theoretical at this point?
Right. So, I mean, it's very speculative.
Okay. Okay, thank you.
How do you create the antimatter in the lab?
I talked about how we do it at SLAC, that we take the electron beam and we use it and some tungsten. When you put an electron beam into tungsten is a very heavy element, and out comes matter and antimatter. But it's a little bit complicated, so, but you need very high energy particles to do it. Let's say that. Is that a good enough answer, or do you have more questions? Okay, next question, please.
Somewhat similar question to one a little while ago, but what is the argument for, or the line of evidence for, self-annihilation of dark matter?
Well, the reason people are talking about it is the data I showed you, which I think is pretty shaky for that. So at the moment, no evidence that's convincing, because you could possibly find astrophysical explanations of that data. The other question is, as people make theories of dark matter, in some of those theories, dark matter annihilations do happen. So we don't know what dark matter is, but we have various extensions of the standard model that introduce particles which could be dark matter. And in most of those theories, most particle physicists pay more attention to a set of theories that have heavy dark matter particles. And those dark matter particles could annihilate because they have some interactions. So there's a story there that you can make a whole consistent story. And the interesting part about that story is those particles could be made at the Large Hadron Collider. So there's a whole story about things that we might make at the Large Hadron Collider that might eventually decay to make dark matter, and we'll see that decay chain. And we won't see the dark matter particle because it will just go drifting on out of our detector, but we'll see that energy got carried off by something that came at the end of this decay chain. So there are theories for which there may someday be evidence, but today there's no evidence.
Thank you.
I have two simple questions. The first one is, so far the black holes are one of the most extreme conditions that we know in the universe.
Mm-hmm.
So would the black hole help us to study this asymmetry more?
Not much, unfortunately, because the asymmetry is in the stuff that isn't in the black holes, right? Whatever went into the black holes again, it's like sorting. If you try and make a theory where the black holes eat up more antimatter than they eat up matter, you're making something that doesn't obey the way the laws of physics work. Because if the laws of physics are the same for matter and antimatter, then black holes will take the same amount of them in as the black hole collapses. So trying to make an imbalance by some dynamics of black holes requires you to invent new physics, which doesn't fit with the physics we know. So again, it's when physicists seldom say that's impossible. When we say that's very, very unlikely, let me give you an example of an unlikely thing. So I say it's very, very unlikely that you could create this imbalance from black holes. Right? It's like saying it's very, very unlikely that you would walk into this room and find all the air under that chair. It's a perfectly possible physical state of the room, just very, very improbable. Right? Because physics didn't work that way. Things tend to want to be distributed in a space where they're allowed. That's called thermal equilibrium. It's the same, it's the symmetries in the laws and the equivalences in the laws that tell you that these kinds of things don't happen. And so because we know the laws of physics for matter and antimatter are these very close mirror images, there's really no way we can make a theory where black holes account for the matter-antimatter asymmetry.
So, thank you. The second question would be, well, this is a wild imagination, that because black hole is such an extreme condition, and we don't know much about it, and is it possible that someday we might discover that actually black hole is the storage pocket for antimatter? Because everything goes in a so-called, we call everything is the matter.
That's the same question said another way. I mean, that's what I was answering in the first answer. That I don't think you can get a consistent, given what we know about how black holes formed and what dynamics went on there. There's something that happened with matter after we had matter. They weren't there from the beginning of the universe. They formed, and they formed out of matter mostly. So the whole story of them forming out of antimatter requires an incredible sorting of matter and antimatter, which just doesn't happen with the laws of physics as we understand them.
Thank you.
You're welcome.